All right, folks, Unit 5 is all about polynomials. We're going to go over some vocab here first. A polynomial is just a collection of terms that looks like addition, subtraction, multiplication, constants, and variables. And those powers on the variables have to be positive integers. We're not going to see negatives, although I'm going to skip down here to the constant. When we see a plus 5, that's equivalent to saying plus 5x to the 0 power. So that degree 0 eliminates that part. And so technically we could have 0 as our power. We just don't see the variable in that case. Talking about powers, degree of a polynomial is the largest exponent of all the terms of the polynomial when we look at it as a whole. And that leading coefficient goes with the term of that highest degree. And then our max number of zeros of the polynomial is equal to the degree of the polynomial. Let's talk about a quadratic real quick, y equals x squared. We know that the degree of this is 2 because that's the highest exponent. And also, most quadratics that we talked about have 2 x-intercepts or 2 zeros. So we're saying the max number of zeros is equal to that degree. It doesn't have to be 2 because we know it could have 1 if our vertex is the x-intercept, or it could have 0 real zeros when we have that parabola floating in space. We've got some imaginary ones. So the max number of zeros we'll see is equal to the degree. So we're going to just practice on these first ones. The first step is finding the leading term. Okay, the leading term is the term that has the leading coefficient or that highest degree. So we're going to go and look for the highest power we see, which is the 7 in this case. So the degree is the 7. Leading coefficient is just that number in front, 14. Constant term does not have a variable, so that's 2. And then our max number of zeros is just our degree that we had of 7. Can't be more than that. It may not be 7 total. When we have multiple variables in a polynomial, we are going to add those exponents to figure out the highest term so we can identify our degree. So going through here, we've got 6, 5, 5, and 7. So this is our leading term. Degree is 7 again, leading coefficient -3. Our constant is 0 since we don't have one. And then our max number of zeros has to match A, so it's 7. We've got this this number 3 here, x squared, our first term. Degree is 2, leading coefficient when you don't see it is 1. Constant term is 2 here, and the max number of zeros, just like we were talking about up here, is 2. Okay, so that last one is all on you. Pause the video, try that. Hopefully you got your leading term was this one. So our degree is 4, leading coefficient is -2. Our constant was the 17, and then our max number of zeros was 4. Next thing we're going to talk about dealing with polynomials is end behavior, which is really what it sounds like. It's what the graph looks like at its ends. Okay? A polynomial can have all sorts of twists and turns in it, but we're going to focus on what's happening way at the left side of the graph and way at the right-hand side of the graph. So we're going to split these into 2 major groups, those with even degree, talking about that highest power again, and those with odd degree, because they share something in common. You'll notice these even graphs here, the first one and the second one, both have arrows facing the same direction, either both up or both down. Whereas odd, the arrows face opposite ways. Okay? The next thing we're going to do is focus on the leading coefficient of our leading term. So that can be grouped into a positive leading coefficient or a negative leading coefficient. And that tells us essentially how the graph ends, whether the graph ends up or whether it ends down, meaning it ends positive or ends negative. Okay, so for a little note here to remember, even is going to mean same direction, and odd is going to mean opposite. And then when we're talking about positive versus negative, okay, positive means we're going to end and negative means we're going to end down or towards the negative side of the graph. So first thing we need to do is identify the leading term. And you're going to see on your homework that abbreviated LT. So our leading term on this first one really is this. So we're going to say our leading coefficient, or LC, is positive, and our degree is 4, which is even. So that tells us even is up and leading, or excuse me, even is same direction and positive is up. So then both of our ends will point up. On the next one, we have a cubic. We've got a leading coefficient that is positive. We have a degree that is 3, so that's odd. I'll write it that way this time. Odd means opposite, and we have to end positive. So if we have to end positive but go opposite directions, that means we have to start negative or start low. Number 3 here, our leading term is that first one again. We've got a leading coefficient that is negative, and then we have a degree that is even. So even, they both need to go the same direction, and the leading coefficient tells us that direction has to be down since it's negative, and then we match that with the even. Okay, so pause the video, try out number 4 for me. This one had a leading coefficient that was negative and a degree that was odd. Okay, so that means we're going to have to end down, and that means we'll have to start up in order for that to be opposite directions. Okay. Now we're going to talk about intervals where a polynomial is positive, negative, or increasing, decreasing. So here, just to tie into what we've been doing, we've got ends that are pointing upwards, both of them. So we know that this is an even degree function, which we can also see right here. And we can see our positive leading coefficient is telling us they're both going up, that positive 1/2. But we're going to talk about where the function itself is positive, and it's not just at the end, it's everywhere above this x-axis. It's kind of our turning point there, our twist. So we're supposed to use the letter labels. If you recall, we've talked about intervals of increasing, decreasing before, and I had to draw out a number line and put those values on your number line when we were dealing with those different inequality statements last unit. But for this one, the letters are already on that x-axis for us, so we don't need to spend the time to redraw it because they already did the work of drawing up to the x-axis what those values would be. But our graph is broken into all these different intervals, from negative infinity to A to B, B to C, C to D, D to E, and E all the way to positive infinity. So when we're talking about positive, we're talking about where this graph is above the x-axis. So that is our first chunk from negative infinity to A, and our last chunk from E onto infinity. Okay, you can write a union with here to represent or. Then we're going to talk about negative. There's only one section for that. That's in between the A to E. And now we'll go back to talking about that increasing, decreasing. Okay, so increasing, decreasing is reading our graph from left to right. So I'm just going to go through here and have you focus on when we're going from left to right, what's happening. So at first, ignore the arrow. The first thing I do when I'm going from left to right is I hit this part of the curve. And the first thing I'm doing if I'm reading it left to right is actually going down. Okay, so it might be helpful for you to put a little arrow on there. And I continue to go downward until this point right here, which matches up with the letter B. So I am decreasing first, so I'm going to go down to this decreasing section and say from negative infinity to B. Now notice I said from negative infinity. I didn't start decreasing at A, it started way at the beginning of the graph. Then my next section on the graph, I am increasing. Okay, so from B to C, the graph is increasing. And then from C to D, the next chunk, I'm decreasing again. And then I end increasing all the way to that positive infinity along the x-axis here. So from D to infinity. Now, what you're going to do to figure out the stopping points and the starting points for these different intervals is identify the turning points. Okay, so I'm going to use that verbiage when talking about these. The turning points is when I switch from decreasing to increasing or increasing to decreasing on a graph. And those turning points are special because they're called relative minimums or relative maximums on a graph. So this one here has 1, 2, 3 different turning points. Looks like my dots got off just a little bit here. Fix those. Okay. And so then there's another turning point name that's an absolute min or an absolute max. And it's exactly what it sounds like. So a relative minimum just means that it's the highest point relative to the points around it. A is higher than that point and that point and that point and that point. And an absolute max is literally the highest point on the entire graph. An absolute minimum would be the absolute lowest point on the graph. And these don't always exist. Okay, so it's often easier to start with the other two. Okay, so our relative minimum is B. That's our low point. And our relative maximums are A and C. From here, we have to decide, are any of those 3 points the absolute highest or lowest? So starting with the absolute minimum, B here is lower than the points around it, but it's not the lowest on the whole graph. So there is no absolute minimum when we see those arrows pointing both down. Absolute maximum, we're looking at A and C, because it has to be one of these if it exists. And it looks like both of those are at the same height, and there's nothing on the graph above it, so both of those would be considered absolute maximums. Number of x-intercepts, just like it sounds, you count the x-intercepts on the graph. So this polynomial crosses 1, 2, 3, 4 times. Now, this word point of tangency is basically where an x-intercept is also a turning point. So that would look like the vertex of a parabola where it crosses, like we were talking about earlier, or the polynomial can continue, but where the x-intercept is a turning point as well. And so for this one, that would be 0. We have, speaking of turning points, 1, 2, 3 total, and those are relative mins and max. And the minimum degree for us, we talked about the maximum degree, or the maximum number of x-intercepts was the degree. The minimum degree can be calculated by taking turning points plus 1. Okay, so we have 1, 2, 3 turning points. One more of that is 4. Now, we did, in fact, have 1, 2, 3, 4 zeros. We couldn't have any more from what we did earlier, but there wouldn't have to be 4. And that's why we talk about the minimum degree being related to turning points rather than being determined by the number of x-intercepts, since we could have some imaginary solutions that show up. Okay? Again, this one, we're going to do this with the same process, starting with the relative one. So the low points are A and C, and the high points are B and D. From there, we're just asking ourselves, were any of those the absolute lowest or the absolute highest? Absolute lowest could be A if it weren't for this arrow. So there's none. Absolute maximum, B and D are at the same height, but all this part of the curve is higher than that. So there's also no absolute maximum. And that's going to be true for any odd degree graph. Okay, that's odd end behavior. There are not going to be any of those because, by definition, they'll go towards infinity both directions. Number of x-intercepts here, we've got 1, 2, 3. None of those were also turning points. Okay, there are 1, 2, 3, 4 turning points, which makes the minimum degree 5. So the number of x-intercepts was 3, but the minimum degree is 5. So if you see this floating turning point, that kind of is what indicates on the graph there are imaginary solutions. But that's what's going on here, why those aren't equal. All right, looking at this one, relative min and max. One more time, we've got our low points of A and C here, relative max of B. And then looking at this, the absolute minimum is C, but there is not an absolute maximum because we have arrows going up. There are 2 x-intercepts here and here. There are no points of tangency. And then the number of turning points are 1, 2, 3 total, which makes a minimum degree of 4. Please make sure your minimum degree also matches your end behavior. Okay? This was an even end behavior because both of the arrows point to the same direction, and that is an even number. Okay, I'm going to have you pause the video and try number 4. Okay, this one had a lot of answers for it. Relative minimum, we had A, C, E, and G. Relative maximums were B, D, and F. And then the absolute maximum did not exist because of this. Hopefully you got that. These arrows would keep continuing up even though it looked like F was higher than the rest of the graph. And then our lowest one was A. And you cannot have an absolute minimum and an absolute maximum for a polynomial. It's not possible. Number of x-intercepts here, we've got 1, 2, 3, 4, 5, 6, 7. One of those was a point of tangency. Number of turning points is 1, 2, 3, 4, 5, 6, 7. And then that makes the minimum degree 8. Now, if you notice the number of x-intercepts says 7, but minimum degree, we're going to talk about points of tangency for a second here. When we see these points of tangency, which is P, these are called multiple roots, or roots with multiplicity that is even. So it could be counting for 2, counting for 4, counting for 6. It's going to be even multiplicity when it looks like a turning point. Okay? An odd multiplicity would not do that. And the easiest way to see that is thinking about y equals, just going to write it like this, x minus 2 squared. I'm using minus 2 instead of just x squared so you can see kind of the transformation. So remember, this would take the graph and translate it to the right 2 units. So then I'd have this parabola. This 2 tells me there are 2 x-intercepts. This factors out to x minus 2 times x minus 2. So the 2 counts for 2. So it has even multiplicity, so times 2. We could also think about that y equals x minus 2 cubed. But the graph of a cubic doesn't look like this turning point. It looks something like this instead. So this is not an even multiplicity. This is an odd multiplicity, so it's only even. But what that means to say is the minimum degree was 8. There's actually 8 taken care of on this graph. 1, 2, 3, 4, 5, 6, and this counts for any even number. So this would be the 7, 8 to get to that degree. And that's really what we're going to practice on these last graphs here, is we're going to answer all these questions, putting together everything we've talked about so far. As a reminder, leading coefficient goes with the right end behavior, whether it ends up or down. The odd or even determined by whether they're both pointing the same direction or the opposite direction. This constant term we haven't talked about yet, but the constant is just the y-intercept. Degree must be greater than or equal to, we just did that one, turning points plus 1. Distinct roots are talking about the x-intercepts. And then how many roots have even multiplicity? Those are the x-intercepts that are also turning points. Okay? And then must there be imaginary roots? That's only if our minimum degree is not equal to the x-intercepts, including those even multiplicity, counting for some that could potentially be missing. So first step, right end behavior goes down, so this one's going to be negative. B, they are both going down, so that is even. The y-intercept right here is below the x-axis, so it's negative. The degree must be greater than or equal to what number? We're supposed to count turning points plus 1. So there's 1, 2, 3. So 3 plus 1 gives me 4, and that matches the even end behavior. How many distinct x-intercepts are there? 1, 2. None of those have even multiplicity. So would there have to be imaginary roots? That's where we're comparing this x-intercepts together with this to decide, did I actually equal 4? So that would be, yes, there would have to be, because I only have 2, and there should be 4. So 2 x-intercepts, 4 total zeros, 2 of them must be imaginary. Over here, the next one, we've got, again, ending at the right, positive. Then they're both going up, so that's even. The y-intercept this time is above the x-axis, so it's positive. The degree must be greater than or equal to 1, 2, 3 turning points plus 1 is 4, which matches our end behavior again. How many distinct x-intercepts are there? 1, 2. And then it says how many roots have even multiplicity? Well, that is 2 as well. Both of them were the turning points as well. So then would there have to be imaginary roots? So we're trying to get to 4 using these. So this one could count for 2, 4, 6, 8, but we just need to get to 4. So here this could count for 2, this could count for 2, and that gets us to 4. So there would not have to be imaginary zeros for this one. All right, last 2 here. Remember, leading coefficient is how it ends on the right. It's going up, so that's positive. They are headed opposite direction, so that is odd. C says the constant term. It looks like the constant here is right at 0, so neither. The degree must be greater than or equal to what? Remember, this is turning points plus 1. So 1, 2, 3, 4, 5, 6. 6 plus 1 is 7. It matches the end behavior of odd. Distinct roots, 1, 2, 3, 4, 5. None of those are also turning points. So yes, there would have to be imaginary solutions. And this is what I was talking about. When one of those turning points is headed towards the x-axis but doesn't hit it, sometimes that's a good indicator that there might be imaginary solutions. And this ended up being a yes. Okay, pause the video, try that last one. We should have gotten negative, odd, because they're opposite, positive, y-intercept, 1, 2, 3, 4, 5 to the degree, matches odd. We've got 1, 2, 3, 4 x-intercepts. One of those is a point of tangency, and so that is a no, because this is 1, 2, 3, 4, 5 to take care of that minimum degree.